All right, welcome back. We're in the home stretch now. Couple lectures to go, and we're all done. Woo. So, yeah, don't get too excited. It's all the hard stuff. One thing I want to point, I'm gonna bail on you guys on Thursday, so I thought you'd be sad about that. I have posted the video lecture for the next class, so there will be no meeting on Thursday afternoon for us. The video lecture is just me doing the same show from 2017, so you can see how much younger and more handsome I was 4 years ago. Okay? Other than that, business as usual. Discussions will still be the same, everything. I just will not be here. So sorry if you hate online lectures, but that's where it'll be. When you come in here and it's pretty quiet, you'll know what happened. All right, so what are we doing? Here to the finish line. This week, we're going to finish up our Chapter 7 stuff. So Chapter 7 is Newton-Euler for rigid bodies. So Newton-Euler, it's sum of forces and now sum of moments for rigid bodies. Last time we got together before Thanksgiving, we started that. And we said, hey, sum of forces equal mass times the acceleration at the CG. So that was just about what we did in Chapter 3. The only gotcha is now we explicitly call out, hey, we're taking those accelerations at the CG. Something we will talk about a little later today is if you've got a composite system, say with mass A and mass B, instead of writing the acceleration at the CG where maybe the CG is here, I got to find that first. You can also write this for this free body diagram as the mass of A, acceleration of A, plus the mass of B, acceleration of B. So this mass up here would be the total mass with the acceleration at the CG. Sometimes it may be easier to break it up. Kind of a horse apiece. You got to do some work to figure out where the CG location is, but it's nice that you only have to find one acceleration. Here, possibly no work to figure out where these locations A and B are, but now you got to figure out two different accelerations. So pick your poison. We'll talk about that later. All right. The new part was the sum of moments. And we said you can take those about any old point P. It can be off in space, it can be moving, it can be anywhere. We said that this was the moment of inertia about the center of gravity times the angular acceleration of the body, alpha, plus some correction term, r, from point P to our center of gravity, crossed with mass times acceleration of our center of gravity, g. So that was the new one. This is, we said, always true. But then we developed a few more techniques to make this one a little easier. And what we're going to look at today is kind of a special case for these. So today's whole lecture focuses on, hey, what if I've got something, like this little guy I just drew here, what if it's pinned at point O? And point O is on that rigid body. Okay? So if it's pinned at a point, everything is traveling in circular motion. We see that really often, and this makes our sum of moments a lot easier. So we talked about, hey, we had very generically moments about any old point P. Then we had sum of moments about point O with O on the rigid body. We said that, hey, this looks pretty similar, but we could have written this as our moment of inertia not about G, but about O, alpha, plus this R vector now from point O to G. crossed with mass times the acceleration of O. So this, if we had any old blob and we were taking the moments about 0.0, as long as O is on the rigid body, this was true. Great. We're going to take this one step further to make life even easier today. O is going to be pinned. So we have rigid body rotation about a pinned 0.0. So if we've got this, that's what we'll look at. Hey, then life gets very easy. I look at my sum of moments about O equation and say, hey, this whole second cross product correction term, acceleration of 0.0. O is pinned. This term just falls out, goes to 0. So we've got our sum of moments about O is just IO alpha. But remember, this is like our special case for rotation about that 0.0. But that's what this whole section's about. Well, you think, well, geez, you showed me the hard way before Thanksgiving, and now we're just going to do the easy stuff. So that's kind of it. We're going to look at special cases that will make life a little bit easier. So we've got on the screen, if we're rotating about some pinned point O, maybe I've got the CG location away from O. So very often, if we think back to what we're going to need to solve a lot of these problems, we're going to write sum of forces equal mass times acceleration at g. So very often we'll need to be able to describe our acceleration at point g. In this case, point O is pinned. We want to figure out how g is moving. This is what we did in chapter 6. We said, hey, the acceleration at g, or any old point on this body, it could be A or B, is equal to the acceleration at some other point I know. Here, let's pick O because it's pinned, plus alpha cross the vector between them from O to G, R from O to G, minus omega squared R from O to G. So we can use this acceleration of a rigid body to figure out, hey, what's happening at point G? First thing we know is that, hey, acceleration of O, pinned, that one falls away. We're left with two terms, alpha R and omega squared R. You think like, hey, I've seen these before, right? Like this is circular motion. That is a perfect circle about point O. Right? Point G is just spinning around and around in a circle. What does the acceleration look like for circular motion? More often than not, we didn't do this in x, y, but we did this in polar and nt all the time. So if we were doing this in polar, maybe I'd say, hey, this is the radial direction from R going away. Theta, positive counterclockwise, this is my u hat theta direction. And then we think back, well, what did we learn for acceleration in polar? We had R double dot minus omega squared R in the R direction. Sometimes we called omega theta dot plus R theta double dot plus 2 R dot theta dot u hat theta. Right. This was what we did in chapter 2. But how does this compare to what we're doing now? Hey, if I'm on a rigid body, as this thing spins around and around and around, my length from O to G doesn't change. So my r dots and r double dots fall away. What I get here is I get a minus omega squared r in the r direction plus r theta double dot. Let's call this alpha in the u hat theta direction. Well, look at this. Same term, minus omega squared r. If you wrote this r from O to G in the r direction, that's all you got. R times alpha, r times alpha. If you went about this and you said alpha was, or this term, let's break this out a little bit, alpha cross r is equal to alpha in the k direction crossed with r in the r direction, r theta k. So I'm starting in k, crossing towards r. I'm left with something in the theta. This is alpha r in the theta. That's that little buddy down there. So what's the whole point of telling you all this stuff? If we have a pinned body, every point on that body is traveling in a circle. So very, very easily in polar coordinates, I can tell you what that acceleration is doing. You know, if I pick a point way over here, really all I need to know is, well, that's point A. All I need to know is the distance from O to A, and then what my angular velocity and what my angular accelerations are. And then I can just immediately say, hey, let's just pretend, like my brain knows from polar, that the acceleration in this r direction, omega squared r, minus those, so points back towards center. Acceleration in the theta direction, boop, alpha times theta. Or, sorry, alpha times theta. Alpha times r. So if you can kind of connect the dots between what we have done with polar coordinates and what we're doing now, it makes life a little easier. If you're not super good at connecting dots, and you just remember, hey, I got to figure out the acceleration anywhere on that body, be my guest. Use that equation, and everything will just fall out naturally. So if you've got a little intuition, great. You can almost shortcut what this cross product term is, because you know, hey, right away, that's going to be alpha r in the theta. This term, that's my radial acceleration, minus omega squared r in the radial direction. So you don't need to be able to just see this and inspect it, but understand it. Like, hey, that's what we've kind of been building towards. All right, done. That's everything. So today is like the easy version of what we did before. So the rest of the time, I'm going to crank through a few examples. What I'd like to do is sum in XY, sum in polar, so you kind of get a feel for both. The technique that we use to solve these guys. I'm going to do the examples out of order. I'm going to start from the back and jump around a little. All right. So here we've got an 80 kilogram disc supported by a pin at A. The disc is released from the position shown. Figure out the angular acceleration and determine the reactions at A. So the reactions at A might look like AX and AY. Hey, you pick the directions, but they better be orthogonal. This might be AR and A theta. For us, this thing is oriented really nicely in XY, so maybe that's a good place to go. All right, so we want to figure out alpha, and we want to figure out our reaction forces. So for these problems, whenever it's like, hey, you got to figure out an acceleration or angular acceleration, that kind of triggers us towards Newton-Euler. And it's the only trick we got right now. Next week we'll learn energy and momentum. So this one, somewhat obvious at this point. Find alpha. And I'm going to use x and y. Okay? So we'll write FBDs. We will sum forces and sum moments. Then we will solve. Very complicated roadmap. But it's kind of the flow that we're doing when we're handling these problems. So FBD. We've got our disk. We've cut it away from its pin support. So at A here, we've got AX and AY, or AR and A theta if you want. At its CG, we've got MG coming down. This is equal to the kinetic diagram. So remember, for the kinetic diagram, our sum of forces are going to follow the CG location. So we need mass times A of G in the x direction, mass times A of G in the y direction. And then we have a little choice to make for our sum of moments. We could sum them about our location G. Whenever I've got a body that's pinned at a point, that's where I'm taking my moments. So this one happens to be pinned at point A. Let's take our moments about A. So I've got I sub A times alpha. This is the foundation of everything we're going to do, right? Everything else should kind of fall from this. If we didn't screw this up, we're in pretty good shape. So, step 2, sum of forces. X direction, AX, equal to, other side, mass times acceleration of G in the x direction. Next, y. So for the y, I've got a y going up, a minus mg coming down, equal to mass times acceleration of g in the y direction. Last one, sum of moments. I've picked point A based on my kinetic diagram, so I've got my sum of moments about A. Positive counterclockwise. So if I'm taking moments about A, I don't have to worry about my reaction forces because they're going to be acting through point A. The only one that can create a moment is my mass, so mass times gravity. But that's going to be negative k direction, so minus mgr, whatever that radius is. And that's equal to a whole bunch of different things, right? Maybe this was I of A alpha. Maybe we had a correction term that we're going to worry about, plus R from G to A, from A to G, cross with mass times the acceleration of A. Right, this was what we wrote for our rigid body that has a pinpoint O. But here I just swapped out O for A. And we said, hey, the acceleration of A is 0, so this term goes away. This is all we really need. All right. So you could certainly start here and start kind of cranking through what we do and don't know. Or this is where you can use a little bit of intuition to kind of feed things along. You say, hey, I've got acceleration, or let me think of my own unknowns here. Don't know ax. Don't know a of g sub x. Don't know ay. Don't know a of gy. mgr, I know those. ia, I got to solve for that, but I can figure it out. And I don't know alpha. Ah, 3 equations, 5 unknowns. Bad news, right? So, the gotcha is that alpha is going to be related to these accelerations. And so is omega. We can figure these out later, or we can use that intuition of that, hey, this thing's traveling a circular path. About point A, right? So, hey, this thing's traveling a circular path. My x direction is actually the radial. So a of g sub x, the acceleration in the radial direction, minus omega squared r. A of g in the y direction, hey, that's my theta direction. This is alpha r. This thing's released from rest. It's initially accelerating, but it has no initial velocity, so that term goes to 0. Ax is 0. This guy, we still don't know alpha. But if you think back to now what we have here, like, hey, my unknowns, I just figured out ax, and I know that ay is really just related to alpha. So then I have 3 equations, 3 unknowns. This intuition is very good. Hey, we don't have that? No problem. We'll get there with rigid body acceleration analysis. It'll tell us this exact same thing. But you can save yourself some time and a little bit of pain along the way. So let's look at our moment equation. Trying to figure out alpha. It's kind of the only thing we don't know in this one. So for sum of moments, what do I have? Minus mgr is equal to ia times alpha. IA, what the heck is IA? IA is the moment of inertia of this disk that's been shifted from the CG over to A. So this is I of a disk plus parallel axis shift. So a disk half m r squared. That's about its CG. Plus parallel axis, I'm moving from the center out to the edge. So I'm taking my mass, and then my d squared, or my distance, is an r squared. So this is 3/2 mr squared. So from this, we got everything we need to solve for alpha. Maybe I come through, cancel some m's, and cancel nr, one of them. Alpha is minus 2/3 g over r. R is 1.5 meters, so this is minus 2/3, 9.81 meters per second squared on g. R is 1.5 meters. Alpha is minus 4.36 radians per second squared. We figured out our angular acceleration. Well, quick sanity check, are we at least going in the right direction? And if I held this thing and I released it, we would expect it to start rotating clockwise. Well, our convention is angular acceleration is positive counterclockwise. So at least we got a negative there. we feel decent about that. All right, so that's that one. We got alpha. We're looking back at our checklist here, what we're trying to figure out. We still want to find our accelerations. They're going to be in our sum of forces x and our sum of forces y equations. If we use what we know, we're done. But if we forgot all about that, we said, I don't remember polar acceleration, no problem. You need to figure out what the acceleration at the CG is. Write that in terms of the acceleration you know. So the acceleration at g is equal to the acceleration at a plus alpha cross r from a to g minus omega squared r from a to g. A is our pin. Alpha in the k direction, crossed with r from a to g. Let me get colorful here. That's just our radius in the x direction. So that is r in the I minus omega squared r in the I. All right, cross product, I, j, k for alpha, k crossed with I, boop, pointing in the j direction. Alpha rj. This guy minus omega squared r in the I. But we already talked that the second we release this thing, it hasn't started any angular velocity yet. So that omega is still 0. So this tells me the acceleration of g in the x direction, or I, is 0. And the acceleration of g in the y direction, alpha r. Take this idea back. That's what we kind of talked about before, right? So that led us to the fact that our acceleration in our reaction force at A was going to be 0. And this one, now we know that the acceleration of g in the y direction is alpha r. We can solve for AY. So my y direction equation, AY equals mg plus m alpha r. We already solved for alpha. I hid that somewhere. My mass, I also don't remember what it was. 80 kilograms. So I got 80 kilograms. G is 9.81 meters per second squared. Minus my alpha, which is 4.36 radians per second squared. And my r was 1.5 meters. AY, if I wrote that down somewhere, 261.6 newtons. So, done. With this problem, what do we have to do? We're trying to find alpha, and we're trying to find reaction forces. Like, that's going to lead us with the Newton-Euler approach. Newton-Euler is sum of forces, sum of moments. So we draw free body diagrams, we sum the forces. Pretty natural. Once we sum these forces, we've got to figure out something about the accelerations. These rigid body accelerations tie together that rotation, omega, the angular acceleration, alpha, with the accelerations at other points on the body. Now that's what we did, wherever it was. That's what we did down here. Say, hey, figure out how those accelerations are all linked together. Angular acceleration, angular velocity, and the linear accelerations. Once you do that, you're free to plug away. Solve for whatever's left over. So, okay, let's keep cranking. I'm going to do this one. So this one's got a rod, and it's got a sphere at the end. We're given masses for both of these. So when I think about what's happening here, I got some mass at the center of this rod. If I think about where it's CG location, I got some mass at this sphere. We got options. So this is kind of where I led us to start the class today. If we think back to that problem I started us with, we got A and B here. My FBD, this is point O. I just changed my mind. OY, OX. And my gravity terms, MAG and MBG. Right? So when we do our sum of forces, let's look at Y here. We can say minus MAG minus MBG plus OY is equal to mass total times the acceleration of the CG in the y direction. So the CG might be here. In order to do this, we got to figure out where our CG location is. I'll call that x sub CG. I'm going to take the datum from the point that I'm rotating about, point O. So x of CG, how do we find this? Well, it's just a mass-weighted position of our various points. So up top, we've got our sum from I equals 1 to n of the mass of I times the x position of I. And that's normalized by my sum over I equals 1 to n of my masses. There you go. That looks super hard, but it's not, right? It's pretty simple. If I look at it now, what am I doing? The first piece of my sum, I've got the mass of A and my position, XA. This would be XA. Plus for my sum, my second piece, MB, its position, I'll just call it XB because I'm lazy, right? All the way to B. Divided by my total mass, the sum of all my masses, mass A plus mass B. So you look at units, you got kilograms, meters. Downstairs you got kilograms, so you're going to be left with meters. It's just a mass weighting of these positions. So figure out whatever you need. That's how you get your location of your CG. To figure out its acceleration, well, it's just a rigid body rotating, right? Your other option, I'm going to go like this. It also equals the mass of A times the acceleration of A in the y plus the mass of B, acceleration of B in the y. This way to look at it is super easy in that I don't ever have to figure out the CG location. Life is good. But I pay the price. I got to figure out two different acceleration points. I got to figure out, hey, how is A accelerating? In the y direction, we know that's alpha XA. And how is B accelerating? Alpha XB. Now I got to track 2 points around. Right? That is a little bit more of a pain in the butt. So however you want to do it, up to you. You got to pay up somewhere. Just thinking about what these various kinetic diagrams look like. So for option 1, I might have I of O alpha, and then at my CG location, mass acceleration of CG in the x. And this is mass total. This is, sorry, crammed in there. M total, acceleration of the CG in the y. Yeah. That's one way to do it. Your other kinetic diagram for method number 2, you can still use your same moment, I of O alpha, but now you got to track both locations. Mass A, acceleration of AX, mass B, acceleration of B in the x. Sorry, I'm running out of space. And then the y, mass of A, acceleration of A in the y direction. And this is mass of B, acceleration of B in the y direction. So incredibly messy at the end. The idea, you get to pick. You do what you think is easier. If you're pretty comfortable figuring out centers of gravity, you're pretty good in statics, hey, go for it. If you think, man, that's a pain in the butt, I'm just going to know all about these accelerations because I'm super good at polar and it's moving in a circle, go for it. This, to me, it's just as easy. So do what you want. All right, so let's actually crank through this example that uses this kind of idea. We got a pendulum, consists of a 10 kilogram slender rod and a sphere of 15 kilograms. So we got the mass of the rod is 10 kg. The mass of the sphere is 15. It's subjected to a moment of 50 Newton meters. And that's going clockwise, so that's going the wrong direction. If the pendulum, it has an angular velocity of 3 radians per second when theta is 45. So at this position, theta is 45 degrees. And it is moving with an angular velocity of 3 radians per second. Determine the reaction forces from pin O. All right. Find OX and OY, maybe. OR, O theta, a little easier, I think. So if you're tasked with finding the reaction forces, you pick 2 orthogonal directions. You give me which ones you like better. Here, I wanted to give you guys a little taste of polar. So that's what we'll do. So just to kind of understand our full things we could do here, our options. This is a composite system. I've got a rod and a sphere. I can treat these independently, or I can treat them as a composite piece. I can do this in XY. I can do this in polar. We're going to do a one-piece composite. We're going to take, why do I want to do this? I'm going to look at M total, alpha about the CG of the system. And I'm going to do this in polar coordinates. Just because we did XY. So, step 1. FBD. I've chosen polar coordinates for myself. We're pinned at the top. We're coming down to our CG location, which I'm going to say is right here. So my forces, I got a reaction O in the R direction, perpendicular to that. O in the theta direction. You wanted x, y? Just take those, rotate them, OX and OY. And then M total times G. That's all our forces acting on this system. Oh, that's not all our forces. We've also got a moment, external moment. 50 Newton meters. That's negative. We'll keep that in mind. All right, this is equal to our kinetic diagram. So for our kinetic diagram, I'm going to take my moments about the pin location. So I need an IO alpha. Now, my mass at the CG is what I'm going to track, because I'm going to look at the total mass. And I don't have to track that in X, I don't have to track that in Y. I can track that in the coordinate system I've chosen. So I've got mass, acceleration, CG, in the R direction. Mass times acceleration of the CG in the theta direction. So this is my sum of forces, sum of moments. So off of this, now what are we going to do? I got to write a sum of forces equation for the R direction. And I kind of think about what I've got here. Like, hey, OR is nice. It's already rotated in that direction for me. And I got to do a little bit of work for this external moment, or sorry, for this external weight. On the other side, my acceleration in the R direction, this is circular motion. So we know what that acceleration in the R looks like. It's omega squared R, but pointing back home. Same thing for the theta. Sum of forces in theta. I got one piece, another piece to take care of. And then over here, my acceleration in the theta direction, alpha times R. We got that. All right, sum of forces. Well, maybe let's find our CG location. So we're starting here. I've got a rod that is some distance, I don't remember anymore. My rod is 600 millimeters. So this distance is 0.3 meters. And my sphere is 600 millimeters plus an extra 100 millimeters for the radius of the sphere. So this is 0.7 meters. All right. So my x of CG, our pinpoint is our datum. Well, it's that weighted, that mass-weighted average. So I've got 0.3 meters times the mass of the rod, which is 10. So I got a 10 on the bottom as well, plus the sphere. That's 0.7 meters, and its mass is 15. .54 meters. We look at that number real quick. Yeah, sure. 0.3, 0.7, 0.54. That gets me kind of right there. It passes the eyeball test, right? It seems like it should be right. So we've got that down. Let's jump back and do our sum of forces. So the R direction first. We've got our reaction, OR. Plus I've got this guy. We knew that this angle theta was 45. Well, that makes life easy. all these other angles are also 45. Right? So 45, 45, 45. So if we broke this into its r and theta components, this would be my r component. This would be my theta component. So in the r direction, it is positive. So it's plus m total times g, and its component is the sine leg. And that's equal to my kinetic diagram side in the r direction. Mass, here's the total mass. I probably was lazy. I should have wrote total, right? M total. M total. Times acceleration in r. And I used big R's and little r's, I'm sorry. All right. So for this acceleration in r, circular motion, minus omega squared r. Right? And this r that I'm talking about is not r at all, but x cg. So we got OR plus the mass g sine 45 is equal to the total mass times minus omega squared x cg. Hey, we're given omega squared in the problem. That was 3 radians per second. We've got xcg, we solved for that. Mass total, I can add 10 plus 15. G, got it. Sine 45, hey, all that's left is to write the answer for r. O sub r, somewhere I've got it written down, minus 295 newtons. So the reaction is not pointing down, it's pointing away from us, right? Well, you can kind of be intuitive on that. As this pendulum is swinging at 3 radians per second, it's trying to like fly away, and you're holding it back. So that to me makes sense. The theta direction. Okay. O in the theta. mg is actually in the negative now, minus m total g, and that in the theta is a cosine leg. Not that it matters because it's 45 here, but just to get it right. That's equal to mass times total mass, acceleration of the cg in the theta. Hey, circular motion. We know that this is alpha r, or alpha x cg. If you didn't know that, no big deal. Just write out the full rigid body acceleration for this rod, and these will come from that. Okay? I'm just 2 minutes left in class, so I got to speed things up. I don't know alpha, and I don't know O, so I'm kind of stuck on this one. Sum of moments about A. All right, what do I got? Reaction forces that don't do anything. External moment in the negative, minus 50 Newton meters. I got an mg, but I only have this cosine component that's so far away, so it's fighting me. Minus m total g cos theta, and its moment arm is xcg. That's equal to I sub O times alpha. From this equation, we're ready to solve. We get alpha. Alpha is equal to minus 16.68 radians per second squared. I fast-tracked that. IO is your composite. It is I of the rod, about 0.0, plus I of the sphere, about 0.0. These both need to be parallel axis shifted back home. So that I don't have totally done. All right, but if we've got alpha, then we can find O in the theta direction. And this is minus 51.6 newtons. Okay? Woo! Sorry, that was a lot, super fast. I will clean this up and I will post it so that you can actually follow along what's happening.